Talk about today is the concept of operators. So, if you say that one detector and the other doesn't click, or both the detectors click, don't think that interference means that one doesn't click. Interference means both. Interference is something different. Interference gives rise to probability that took place at the time. That's why I say the sum or the whole is not the sum of its parts. It's different. So please do submit your homework by tomorrow morning. Alright, now I would like to talk about operators. So we've already seen operators in disguise. So now we're going to formalize the treatment of operators. Suppose I have a quantum state psi, okay? Now this is a totally general state. It need not just be the polarization of the photon. It could be anything. It could be the spin of an electron. It could be the path of a photon. It could be the charge of an electron. It could be anything. We motivated ourselves using the polarization concept. But the quantum state could refer to anything. Any quantum object. Like a single photon, an atom, an ion, an electron, the path of a photon, to any degree of freedom that you're talking about. Okay? So suppose an object, a quantum entity, has a state psi. Okay? Now I'm going to make a generic diagram. A generic diagram means I'm going to make a logical flow chart. I draw a line and I say that there is a quantum state psi that is present here, and there is some action that takes place, and after this action the new state is psi dash. Okay. Just like a photon that has a certain polarization state sees an optical element, a half-wave plate, a polarization beam splitter, a quarter-wave plate, or a beam block, or something, and a new state is prepared. So this original state transforms into a new state. And from our discussion of polarization, alright, let's get settled down, please. No commotion. Please, let's settle down. From our discussion of polarization, we've noticed that this optical element is represented by a matrix. Okay? So the general name for such a matrix is an operator, and it's generally denoted by some letter, like O, and you put a hat on top of it. Okay? So it's O hat. It represents an operator. This operator acts on this quantum state to give you a new quantum state. The state has transformed under the action of the operator. Of course, if this is represented by a column vector, this is represented by a matrix of the correct dimensions, of the correct size. And mathematically, this flow chart is represented by a quantum state psi, and an operator acts on the state to give you a new state. Okay? Simple. Suppose you have a state that comes in psi, and you have many operators, O1, O2, all the way up to OM, and you want to find the state here, psi dash. So what you would do, you would take your original state psi, first O1 acts on it. It's followed by O2 acting on it. Okay? So look at the time ordering. The operator that acts first comes to the right, and it acts on the ket, followed by the operator that acts after O1, and it comes to the left, all the way up to ON. and you get your final state, psi dash. So these are cascaded operators. And all of these operators, when they are cascaded, they are strung together, they form an effective operator, right? So you can write O effective equals your first operator followed by the second operator, third operator, all the way up to your last operator. So psi dash is O effective operator acting on psi. So remember this word time ordering. The time ordering of the operators is extremely important. In general, O1 followed by O2 will give you a different state than O2 followed by O1, which means that these two operators are in general not the same. Just as if two matrices, they don't commute. The matrix multiplication is not a commutative process. You change the order of matrix multiplication, you get a different matrix. Okay? So in order to capture this phenomenon, we define in quantum mechanics an operation between two operators, O1 and O2, by putting a comma between them and enclosing them in square brackets, and this is defined as O1 multiplied by O2 minus O2 multiplied by O1. In general, this operation between two operators is not equal to 0 in general. Okay? This operation is called the commutator between the operators. If the commutator between the operators is 0 somehow, it could be 0. In general, it's not 0. But there are matrices whose commutator can be 0. If the commutator is 0, we say that the operators O1 and O2 commute. Okay? In general, the commutator is not 0. In general. And in linear algebra, the commutator is something innocuous, but this commutator has deep significance in quantum mechanics. All of quantum mechanics and the mysteries of quantum mechanics are explained in many cases by the fact that the commutator is not 0. And we learn about this in this course. Alright, let's talk about a few operators. Let's look at the unitary operator, or the unit operator. Unit operator. Suppose I have a state psi and the unit operator acts on it. The unit operator is represented by a bold 1. It's an identity operator. Nothing happens to the state. So a photon just traveling in vacuum, it's a quantum object. If nothing happens to it, the unitary operator for this process, the operator for this process is unitary. Is unit operator, sorry, not unitary, it's unit operator. Unit operator means do nothing to the state. Alright. I also want to define an object that is called the adjoint operator. Suppose I have an operator O that acts on psi to give me psi dash. Okay? So this is state psi, the operator acts on it and the output is psi dash. The state has transformed from psi to psi dash. Now every ket has a dual. That's the bra. So the bra for this, or the dual for this is psi dash, bra psi dash. The dual for this vector is bra psi. So in the dual space, there must be an operator that takes psi, bra psi dash. The dual of this operator is denoted by the same symbol with a dagger sign. Dagger. Okay? So this is called O dagger. O dagger is the adjoint of O. Both of these, this operator and this operator are adjoints of each other. Okay? The adjoint of the adjoint, of course this is O itself. We'll learn more about adjoint operator, but this is a definition. So in the Hilbert space, in which kets live, quantum states live, you have operators that act on the kets to give you new kets. In the dual space, kets live, and there are operators that act on the kets, on the bras. Sorry, in the dual space, bras live. So there are operators that act on the bras to give you new bras. Okay, and notice that this operator always comes with the vertical line. So here the vertical line is made. So adjacent to the vertical line you place the operator. You don't write O adjoint acting on the bra, right? This is wrong. This is wrong notation. All of this notation is due to Dirac from the 1930s. It's called the Dirac notation, the bracket or the bracket notation. Okay. Of course, I can also write, say, some bra phi. I can have an operator A acting on phi to give me phi dash, a new bra. Okay. And if I want to write this in its dual space, then I would write A dagger acts on phi, ket phi to give me phi dash. Alright? So in the dual spaces, the operators are adjoints of one another. Okay? So far so good? And we'll do plenty of examples, so don't worry. So everything will seep into your minds and your consciousness in a slow, steady manner. Don't worry. It's going to be a slow process. Now let's look at some more operators, examples of operators. Let's look at the rotation operator. I would like to move back to the polarization of a photon, of a single photon. Clearly, the polarization of a photon is described by quantum state which lives in a two-dimensional Hilbert space. And I would like to draw a diagram. This is the x-axis, this is the y-axis. Okay? Just for reference. So if I have a quantum state which is ket h, now ket h doesn't live in the xyz space, remember. Ket h lives in a Hilbert space. It doesn't live in a three-dimensional Euclidean space. It lives in a Hilbert space. So this diagram that I've drawn is just for illustration. Okay? So there is a ket h that belongs to some two-dimensional space. And what I would like to do, I would like to rotate this operator, this state into the 45 degree state. Okay. So of course I would have to make an operator act on the initial state. So the rotation is achieved by an operator. So suppose I represent that operator, rotation operator by R. Okay. Put a hat on top of it, R. Now, different people use different rotations. Since the rotation is about an axis which is the z-axis, okay? So generally people can write a small z here if they want. And the rotation is through an angle of 45 degrees, okay? So this is the angle of rotation. So this is the rotation operator, and this is how I have denoted it. Okay? The argument is 45 degrees, and it's about the z-axis. But remember that x, y, and z, the polarization vector, the quantum state vector, does not live in the x, y, z axis, the conventional notion of the Euclidean space. It lives in the Hilbert space. It's a two-dimensional space. Okay? So if this operator acts on ket h, we say that the operator is acting from the left because the operator is to the left of the state. The result is the state 45 degrees. Okay? If Rz pi by 4 acts on 45 degrees, what should I get? I will get the vertically polarized state, get B. If Rz acts through an angle of minus 90 degrees on the vertically polarized state, I would get ket H. And so on. Okay. So I'm taking rotations, positive angles to be clockwise rotations. I'm using a right hand convention. I have to define my convention. Likewise, if I look at this relationship and I want to find the dual of this operator equation, what I would do, I would take the corresponding dual vector, which is the bra. So this becomes bra 45 degrees. This equals some operator that acts on bra h. And what is that operator? It's going to be the adjoint of this. Okay? So I would write Rz pi by 4 and I would put a dagger with it. Alright? The dual equation for this operator equation in the Hilbert space is going to be bra B equals bra 45 degrees being acted upon by the operator Rz dagger. Right? And now the operator is acting from the right. Okay? So this is all notation. We're building the formalism, we're building the recipe to understand quantum mechanics properly. Likewise, if I have some state which is linearly polarized, okay, at an angle theta with the horizontal, and onto this state acts the rotation operator which rotates the state through phi, what is going to be my output state? What should I write on the right hand side? Which ket, what I should write a ket first of all. What should be the angle of the ket? What should be the state? The initial state is theta. What is the new state? Theta plus phi. Theta plus phi, because the rotation is now to phi. So this is the angle of rotation and this is the angle, this is the axis of rotation. This is the angle through which rotation takes place, and this is the axis. Suppose I have the operator O1 followed by O2. Okay, and this acts on psi. O2, O1 acting on psi to give me psi dash. Now what should I write as the dual of this operation? What is bra psi dash going to be equal to? It's going, something is going to act on bra psi, right? What is going to act? The adjoint of all of this. Okay? O2, O1, dagger. And the adjoint of a product of operators is the product of the adjoints but with the reversed order. First of all, which means that first of all, O1 has to act on psi, or O1 dagger has to act on psi. So O1 dagger acts on psi followed by O2 dagger. Okay? So you have to preserve the time ordering. The time ordering is essential because matrices don't commute in general. You change the order of the matrices, the matrix, the effective matrix changes. Matrices don't commute. Operators don't commute in general. So in the Hilbert space or in the direct space as it is called, O1 acts on psi to give you some intermediate state. Say psi double dash. And then O2 acts on psi double dash. So in the dual space, the adjoint of O1 must first act on bra psi to give you bra psi double dash. And then O2 dagger acts on it. So you have to reverse the ordering when you go from the direct space to the dual space. Okay? Now something very interesting. Suppose I have ket H and RZ 45 degrees acts on it. Okay? But I have two operators acting on the state. One is RZ through a 45 degrees angle followed by another identical operator. Okay. So what's the final output? Ket D. Now let's take the Now let's take the inner product of V with ket A, with ket H. Inner product is written like this. So I can write this as ket H RZ pi by 4 RZ pi by 4 and bra H, right? This is something I can write. Okay, so I have taken the inner product of the right hand side with ket H to give me the inner, I always say inner product between two kets. Okay, but one of the kets is represented as in the dual space. So this is an inner product. I take the inner product of the left hand side with ket H. The result has to be 0 because the horizontal and the vertical states are orthogonal. So this has to be 0. Okay? So this is these are some kind of gymnastics that we should all be familiar with. Okay. However, keep this expression in your mind. If I have RZ pi by 4 acting on ket H, I get ket 45 degrees. Now the dual of this operation is that I have bra 45 degrees and this must equal bra H being acted upon by RZ pi by 4 dagger. Okay. Now, if I take the inner product of cat 45 degrees with another cat 45 degrees, what should I get? 1. Okay. So what I am going to do, I am going to take the inner product of this cat with the corresponding cat here. So what do? I just concatenate these two expressions and I draw H RZ pi by 4, right? This is simply this. This cat is simply this. RZ pi by 4 and cat H. Okay. But this has to be equal to 1. Do you remember? Do you notice what I've done here? So this has to be equal to 1. Now what does this mean? If this has to be equal to 1, this operation has to be equal to something. It has to be equal to the identity. Because if I leave this bra H alone, the result of all of this operation which I have written in the square brackets has to give me cat H, because only the inner product of cat H with itself is 1 and I have to get 1. So this, whatever I've written in the square brackets must equal cat H, right? So whatever I've written in the square brackets must equal cat H, because the inner product of H with itself is 1 and I must get 1. Now what does this mean? This means that this operator multiplied by its adjoint must give me another operator which is identity, the unit operator. Okay. So the operator multiplied by its adjoint, R multiplied by its adjoint, gives me identity. Okay. In other words, if I take R and find its inverse, now if I have two matrices, their product is identity, then one matrix or one operator must be the inverse of the other. So if I take this operator and find its inverse, it must give me the adjoint. Okay? So matrices that obey this relationship, in which the inverse of a matrix is equal to the adjoint, or the adjoint is equal to the inverse of the matrix, they are called unitary operators. Unitary operators are operators generally denoted by U. They are such operators that their inverse equals their adjoint. Okay? Or you can also say that U multiplied by the adjoint in either order gives me the identity operator or the unit operator. This is how we define unitary operators. Not all operators are unitary.
The inverse of the dagger is also...
Right. The inverse, you take the inverse of both sides. Dagger, inverse, gives me U. So, if A is the inverse of B, then B has to be the inverse of A. This is called the self-reflexive property of the inverse. Okay. So this is how we define unitary operators. The rotation operator, as we've observed here, is a unitary operator. Okay? The rotation operator is a unitary operator because its adjoint is equal to its inverse. Some more examples. An alternative definition of unitary operators. A unitary operator denoted by U is such an operator that when it acts on any state, the best this operator can do is that it keeps the state unchanged and only adds some global phase to the state. An alternative definition of a unitary operator. When it acts on a state, it keeps the state unchanged, may only add a global phase, which can be 0. Now what we have to do, we have to check whether this definition equals this definition. Right? Now we also know that we can define the norm of a vector or state. Right? A vector is a state in the Hilbert space, okay, or a ket. So if I have a state psi, I want to find its norm. Okay? I want to find the norm of this state. I just put 2 lines on each side. This is the norm of the state, norm of the vector. It corresponds to the length of the vector in classical sense. Okay? So this is defined as the inner product of the state in itself. Okay? If the state is normalized, then the inner product is 1. Okay? This represents a normalized state. And I've already mentioned that all physically realizable states must be normalized, because this inner product has something to do with the probability. Okay? So this is how we define the norm of a state. What a unitary operator does is unitary operators preserve the norm. Preserve the norm. They keep the length of the vector the same, or the norm of the vector is unchanged. Let's see the meaning of this statement. The unitary operator acts on psi to give me the same state, albeit with some global phase. Okay, even though with some global phase. Now what I want to find is, this is my output state, okay? All of this is my output state. Suppose the original state was normalized. Okay, this is what this means. The original state is normalized. What I want to find is that after the unitary operator has acted on the state, what's the norm of the new state? This is what I want to find. Okay? This is unknown. This is what I want to determine. Now, psi dash is given by this expression, ei beta, right? I want to find the corresponding bra. So what's the dual of this vector? It's just going to be bra psi multiplied by e minus iota beta. Now these are just numbers, these are just scalars, they just give me 1. So I get psi, right? And this of course is equal to 1. Or the norm, whatever the initial norm was, the final norm of the final state is going to be unchanged. So this kind of operator which obeys this relationship is a unitary operator because it preserves the norm. Okay? Now what we would like to find is whether this definition matches this definition. So I take this vector and I find its dual. the dual of the left hand side is just going to be graph side multiplied by u operated upon by u dagger, right? And this must equal, the dual of this must equal graph side and e raised to minus iota. Okay? Now I take the inner product of this object with the cat. This equals ei beta acting upon psi. Now this is just a number. This gives me 1. I get. Now if this has to be true, if this inner product must equal this inner product, then this operator, what should this be equal to? Identity, right? Hence, the unit operator and its dagger must be inverses of one another. And this is what we've shown over there. And can you see for yourself that the rotation operator does nothing to the length of the vector. It just rotates it. Okay? It just rotates the vector. So the length of the vector remains unchanged, or the norm of the vector remains unchanged. Only its orientation changes. So the rotation operator is indeed a unitary operator. Okay, any questions? ये देखो, ये वाला रिलेशनशिप है, इसका डुअल लिखिए. इसका डुअल ये होगा ना. U dagger acting on psi gives me the dual of this, which is graph psi multiplied by e raised to minus iota. Okay. Now I find the inner product between this and its dual. So I just write this expression here. I write this expression here. Okay. Now this must equal this. So I write this here. This must equal this. I write this here. These cancel out, and I get the norm of the original vector. But the norm of the original vector is 1. And if this thing has to be equal to this thing, then what I've written in blue must be equal to identity. Which means that u multiplied by its dagger must equal identity. Which means that the inverse of u must equal the adjoint of u. And this is what unitary operator means. Okay? So if this is true, then that should be true. So all of these definitions are equivalent. Physically, what the unitary operator does is that it preserves the norm of a quantum state. It does not change the length of a vector, in other words. In linear algebra, rotation operators are unitary operators. But the difference is that in linear algebra, you probably have studied operators only with real entries. Okay? Now these unitary operators can have complex entries. Complex numbers as entries. Alright, any more questions? It's very important that these concepts sink into your bloodstream. And then it diffuses to your hand as well, because unless you practice with your hand, you will not be able to understand all of this. So studying quantum mechanics is complete coordination between your mind, eye, probably your ears and your hand. You must use your hands. You must practice. Without practice, nothing will seep in. Okay, now we would like to talk about another operator. Projection operators. Let's meet at 6. Sharp 6. Now we're going to look at another operator. So what we've been looked at? So we've looked at the unit operator, right? We've looked at unitary operators. We've And examples of operators are rotation operators. And now we're going to look at projection operators. So unit and unitary operators. Okay, listen. Unit and unitary operators are classes of operators. Rotation, projection operators are also classes of operators, but they are categorized differently. For example, a rotation operator is unitary. Okay? A projection operator is not unitary. So these come from physics and these come from mathematics. So by looking at the properties of different operators, that is the properties of matrices, we can classify operators as unit, unitary, Hermitian, anti-Hermitian, anti-unitary and so on. But these are physical classes of operators. So a rotation operator is unitary in the mathematical sense. Now we're going to look at the projection operator. And what does the projection operator mean? Okay. Suppose I have a quantum state psi which is written in a basis as CH ket H plus CV ket V. Now if I take the inner product of this ket with H, but if I take the inner product of psi with H, what do I get? CH. Good. If I take the inner product of psi with V, what do I get? CV. So these probability amplitudes are in fact the inner product of the complete state, which is a superposition with the basis states. Okay? Hence, I can write this state as CH can be replaced by this inner product ket H plus agreed? There is no harm in writing this original state in this form. Okay. Now this object is an inner product. This is an inner product. Is this object a scalar or a ket or a bra? It's a scalar. It's a number. Like 1, 2, 3 iota minus iota, 1 over under root 2, 3 over under root 3 iota. So it's a number. It's dimensionless. It's number. It's a number. So it doesn't really harm if I take this number and write it after the ket. Okay? So what I'm going to do now, I'm going to play a trick. First I'm going to write this ket H, and then I'm going to write this inner product after it. Okay? So first I've written the ket and followed it by the inner product. Okay? Likewise, first I write the ket followed by the inner product. Okay? I've just changed the ordering because if I have a number, I can take it before and after the vector. It doesn't really matter. Okay? It's translatable, it's porous. Okay. Now look at this. Now what you notice here, all of this has to be equal to psi. Okay. Now operators have another property that I forgot to tell you earlier. If I have an operator O1 plus another operator O2 acting on a quantum state psi, then this operation is linear and it's distributive, which means that this must equal O1 acting on psi plus O2 acting on psi. Okay? So the addition of operators is distributive. Likewise, the addition of states psi1 plus psi2 is also distributive. Okay? So operators and states have these properties. Both of these statements are often summed up by saying that quantum mechanics is linear. Okay. Therefore, if I have small numbers here like C1, C2, I can have C1 and C2 here. The numbers, the scalars, they are porous, they can move anywhere. They can't jump over plus and minus signs, but they can move between operators and numbers, right? Likewise, if I have C1 here and C2 here, I'll have C1 here and C2 here, right? So both of these expressions are generally summed up by saying that quantum mechanics is linear. Okay? However, remember that operators don't commute. You cannot reverse the order of the multiplication, but you can reverse the order of the addition. Now, if you look at this expression, you can play another trick, and this is the power of the Dirac notation. You can write this as the following. You can take cat H, bra H, plus cat B, bra B, and all of this acts on cat psi. In other words, I factorize cat psi and write it right at the end. Okay? Fine. Now this object, okay, now remember this is a state. So the right hand side must also be a state. Now this is a state and something is acting on a state to give me a new state. So this must be an operator. This object must be an operator. This operator acts on this state. Okay? This operator acts on this state to give me this. And this operator acts on this state to give me this. Okay?
So what's the cross here?
What's the
What's the cross? What is it?
clause? Okay. What does this? This means that I write cat H followed by bra H. Right? This is what it means. I just out of convenience or out of writing felicity, I just write this as cat H. Okay, it's not a cross. So this is an operator, acts on this state to give me this state. Remember, look, this is a state. A number with a cat is a state. A number with a cat is a state. So this equals this operator acting on this state, and this object equals this operator acting on this state. So this operator, I represent this by PH, and this I can represent as PV. Okay? So PH acts on psi to give me this object. PV acts on psi to give me this state. These operators are called projection operators. Okay? And let's see what are these projection operators doing. I give you 1 minute just to think about this before we move on. pH I have defined as cat H followed by bra H. Okay? This is what I defined the projection operator as. PV I have defined as cat B followed by bra B. Okay. Remember, this is not a state, it's an operator. Let's see what happens when PH acts on get side. Okay. An operator acts on state. So let's see what happens when this projection operator, which I have identified over there, acts on the state. Okay. So PH is now acting on psi, which in general terms is given by CH ket H plus CV ket V. Okay. Now PH is ket H bra H acting on CH ket H plus CV ket V. Okay. Now this is a superposition of states. By using this linearity principle, this operator will act on this state and it will act on this state. Okay. So CH is a number, it's porous, it can move anywhere you like in this term. So I write CH followed by ket H, bra H, and what am I left with here? Ket H.
Sir?
Okay. Plus CV, it's a number, it's porous, I can put the CV here, then I write this operator ket H, bra H, acting on this state V. Okay, any confusion at this point? Okay.
सिर्फ मैं वही बोल रहा था कि ये H कैट अगर ड्रा नहीं हम कैसे कर सकते हैं?
Sorry?
ये जो ड्रा और कैट हम मल्टीप्लाई कर रहे हैं ये
मल्टीप्लाई कुछ नहीं करना, लेकिन इस ऑपरेटर को इस पर एक्ट कर रहा हूँ. ठीक है, मैंने ये देखो, इसको मैं ब्लॉक बॉक्स में लिखता हूँ. ठीक है, ये जो बॉक्स है वो ये आ गया. ठीक है, दिस बॉक्स is taking this operand. This operator is acting on this state. The state I write here. I don't put two vertical lines. Two vertical lines in the direct notation are just subsumed as one. So this thing is simply a shorthand way of writing ket H, bra H, acting on H. So I don't write these two vertical lines, I just subsume one of them. Okay, this is just the Dirac notation. Okay, so now this operator is acting on this state and the same operator is acting on this state. And it's linear, right, because of this rule.
So my question was, in the previous example of the CH or CV, you shifted them back and forth. This can be अगर आप पहला वाला जो कहता है वो एक पोजीशन आगे शिफ्ट करना.
So can I get bracket here? Is the operator is the same as the bracket itself?
I mean, what I want to find is that if I have this operator, I acted on a state. This is my starting point. I've defined my operators over there. PH is defined like this. So this operator is now acting on the state. I want to find out the action of this operator on an arbitrary state. What does it do? Okay. So now, notice, even though this were an operator acting on a state, I have created a bracket here, an inner product here. Right? So I can at my own will choose whether I want to take this think of this as this operator acting on the state, or I want to think of it as this inner product being multiplied by the state. It's my choice. So now this is an inner product. And what is the result? This must result in a number, in a scalar, which is 1. So I just get CH, get H. Okay? Now this is also an inner product. What's the result of this? 0. So my answer is CH, get H. So my projection operator acts on an arbitrary state and it just picks up the horizontal component. Right? So physically, what this is it's just like a linear polarizer whose axis is along the horizontal. So an arbitrary state comes in, the output is just CH cat H. Okay? It's just like a horizontally inclined polarizer. That's why it's called a projection operator. It picks up the horizontal component of the entire state In other words, it finds the projection of the state onto the horizontal axis. It just picks up this component, right? Question. If there are n photons coming in, all in identical states, आप बताएं how many photons do you expect here?
CH square.
CH modulus square. So this is a polarization operator. So this projection operator models a horizontal polarization. Every optical element is modeled by an operator. This polarization operator or projection operator models a horizontal polarization, which is physical, which is in the lab, which is something that is tangible. Quantum mechanically, it is just this projection operator. Likewise, the vertical operator is just going to produce CV cat B as the output. And it's clear. PV acting on psi is just cat B, bra B acting on this state. Now this is a number which is equal to CV, and I get CV cat B as the output. So this is a vertical polarization. Now projection operators are very nice operators in the sense that it's not necessary that you can project onto the horizontal axis or vertical axis. You can project onto any state like that. So I can have a projection operator on the state phi. This is defined as ket phi, bra phi. Okay. I can have H, I can have V, I can have 45 degrees here, I can have 135 degrees here, 20 degrees, any state I would like to project on. I can have an elliptically polarized state, I can have a superposition here, any state. So this is the general definition of a projection operator. And projection operators have a nice property. If I take a projection operator like this, and I take the square of it, the square of an operator is just P phi followed by another P phi. Okay, so what is P phi? P phi is ket phi, bra phi. Okay, what is this P phi? It's ket phi, bra phi. So I put another ket and another bra, right? Now what is this object?
1.
If the state is normalized, if this phi is normalized, this is going to be 1. So this just becomes ket phi, right? This becomes P phi. In general, for a projection operator, P phi raised to power n, that is the P phi acting n times, gives me back P phi. Hence, the projection operator is idempotent. An idempotent operator is an operator which, when acted multiple times, gives you the same output. Okay? So idempotent operators come here in this category. They are mathematical property, idempotent. So idempotent operators have a special place in quantum mechanics. If I have a state psi, I have a projection operator PH, okay? What's the state that I get here? आप बताएं, यहाँ पे क्या state आएगी? Get H with a CH, right? Okay. Now I have this state, I put another projection operator. What do I get? I get the same state, right? Nothing happens. So I string many projection operators all along the same axis together, my state remains unchanged. Okay, this is like putting many horizontal polarizers back to back, back to back, back to back. So if the state has a tendency to change because of the environment, then if I put the horizontal polarizers again and again, putting a horizontal polarizer is just like putting a PAHB, right, a polarizing beam splitter, and blocking its vertical channel, right? You block the vertical channel and let the horizontally polarized photons go through. Okay, this is what a horizontal polarizer can be modeled as. It's a polarizing beam splitter whose vertical channel has been blocked. So the new state is prepared every time and it's ket H, proportional to ket H. So you put many of these polarizing beam splitters together, the state remains unchanged. It always remains this. Which means if you're measuring the state again and again, if you're continuously measuring the state does not change. This is called, in quantum mechanics, the Zeno effect. Right? It's the quantum version of saying that a watched pot never boils. अगर आपने कोई हंडिया चढ़ाई और उसको आप तकते जा रहे, देखते जा रहे कि इसमें उबाल आए, इसमें जोश आए, वो कभी उसमें उबाल और जोश नहीं आएगा. अंडा उबालने की कोशिश करेंगे, आप देखते रहेंगे देगची को, वो कभी नहीं मिलेगी. Its state will be preserved. Okay, so this is called the quantum Zeno effect. Continuous measurement keeps the state unchanged because you're continuously projecting it onto the horizontal axis. Okay, you're continuously creating the new state, which is CH ket H. Okay, another interesting observation. We know that this product between two kets, it's called an inner product, right? I have ket psi, ket phi, I take the inner product, it's a number, it's a scalar, it's called the inner product. Right? This object, ket psi, an object like this, okay? A ket followed by a bra. This is not a number, it's an operator. Okay? This kind of operator is called an outer product. Okay, an outer product. And we'll see how to represent this. We'll learn this.
Sir,
Yes.
can we call it a vector in the Hilbert space?
It's not a vector. This is a vector. This is a vector. On its own is a vector. Psi is a vector. These are vectors. Kets are vectors. But this is not a vector. This is a ket followed by a bra. All of this is going to give you an operator. And we've seen that the PH, the projection operator, is an outer product. The projection operator is a special kind of outer product in which the label here is the same as the label here. Okay.
But over here we get CH, ket H, right? So ket H is a vector.
So this acts on some state to give you a state. It must be an operator. So this object, right, must act on some state, chi for example. Right? So this is an operator. It acts on some state which I have represented as chi, and I should get as an output another state, because now an operator is acting on a state, I should get another new state as the output. Now what is my new state? I just use the gymnastics and the aerobics of the Dirac rotation. I write this ket followed by this bra followed by this ket. Now this becomes an inner product. This becomes a number. Right? Let me call this number D, okay? D, some number, some scalar. So this object is D times this ket. So the output is a state. The operator acting on a state gives me a new state, where D is given by this inner product.
ये x है psi है?
ये
हाँ जी।
chi. The Greek alphabet has only 26 letters, so I will probably use all of them in this course.
मेरे पास वो दो है।
ये psi है,
Psi.
ये phi है, ये chi है.
सर ज़ेनो इफेक्ट कॉन्ट्रडिक्शन ही हम पहले जो हमने एक पैराडॉक्स एस्टैब्लिश किया था कि मेजरमेंट काइंड ऑफ alters the state.
So whatever state you have input, right? You are getting a new state, you alter the state. Now you are measuring along, your measurement axis is the same as the state. The measurement does not always alter the state. If your measurement is along the state, which means this cat age, bra age is along cat age. So if this input is an eigenstate of this operator, the output will remain unchanged. Okay? Now one thing I would like to finish off this class with, I mean this is too short time for a quantum mechanics class. Right? So we know that the transforming matrix for this half-wave plate goes like this: 1, 0, 0, minus 1. We know this. And what this half-wave plate does is that if you have an input state that is at 45 degrees, okay, and you act upon this, the matrix for the half-wave plate, what do you get as the output? Minus 45 degrees. Okay? Now you're rotating the state. Your input state is at plus 45 degrees linearly polarized, and you act upon this matrix, and your output is minus 45 degrees. Let's work this through. So you have the half-wave plate. The matrix for the half-wave plate is given by this. The 45 degrees is given by 1, 1, 1 over under root 2. What's your output? 1 over under root 2, 1, minus 1, which is simply minus 45 degrees, right? So what this half-wave plate has done is, if I draw a diagram, this is my x-axis, this is my initial state, plus 45 degrees. It's rotated this state through 90 degrees, and I have achieved minus 45 degrees. So is this matrix the representation of the rotation operator?
Yes.
Okay. So if I denote the rotation operator, Rz 45 by 90 degrees is my rotation angle. Right? Sorry. Dagger. And this acts on 45 degrees, or minus 90 degrees is my rotation angle, because now I'm taking anti-clockwise rotation. So I get minus 45 degrees. Okay? So if my rotation operator rotates the state to minus 90 degrees as it does for a half-wave plate, this is my output. However, if I take this rotation operator and I rotate through minus 90 degrees again, but now my input state is cat h, what should my output be? Minus cat h. However, in this case, if I have a half-wave plate and my input state is horizontally polarized, what's my output? It means unchanged. Because now the state is parallel to the fast axis of the horizontal wave. Hence this operator, this matrix or this operator is not the same as this rotation operator. Because what the rotation operator should do, it should take any state, any input state, and must rotate it by minus 90 degrees. But that's not what the half-wave plate does. So this half-wave plate, this matrix does not represent the rotation operator. The operators are universal. The rotation operators are universal in the sense that they can take any input state and do the same, have the same effect on all possible input states. So the half-wave plate is not a rotation operator. The rotation operation is achieved by other physical mechanisms, on which I have constructed a quiz for you on Monday. Okay, I'll ask sequential questions which will lead you through to finding out the rotation operator. Alright, so any question, you have to be crystal clear in your concepts, which we are going to cover in these weeks, because these are the foundation. Yes?
एक बार क्वेश्चन बता दीजिए how rotation operator is different from the matrix.
From this matrix, ये देखो, ये हाफ वेव प्लेट का मैट्रिक्स है, ये कैट एच बैक होकर कैट एच दे रहा है, लेकिन रोटेशन ऑपरेटर कैट एच बैक होकर माइनस वी देना चाहिए. So this should not represent the rotation operator. So half wave plate is not a rotation operator. Okay. So let's meet on Monday, and on Monday there is going to be a quiz. Please submit your homework by tomorrow.